In quantum mechanics, we generally come across two types of uncertainty relation. One is the position momentum and the other one is energy time. In position momentum, delta x and delta p, it represents how much the values can vary when we measure them. In energy time, delta E represents a similar quantity in the context of energy, but what about delta T? Time is not something which we measure in the same way as position, momentum, or energy. It is just a parameter that tells us how things evolve. So, what does it actually means? That is what we are going to find out in this video. By the way, energy time uncertainty principle is a unique one, and it is not same with the position momentum pair or any other type of uncertainty relation. First, let us try to understand the meaning of delta x or delta p or delta E. If you have a quantum system, let us make identical copies of this system. And in these identical copies, let us measure the position in all this system. For this measurement, we will have a distribution. And for this distribution, we can calculate the mean and we can also calculate the standard deviation. This standard deviation, it is what we refer to as the delta x. Therefore, delta x is not a single shot measurement error, but it's a property of the distribution. Unfortunately, in quantum mechanics, we call this as uncertainty of that variable, which is a very sloppy term. Now, if you measure momentum in this identically prepared quantum system, we will have a distribution, and the standard deviation of the distribution, it is delta P. Then we can have a similar measurement for energy also. Now you can see, for time, we cannot have such type of measurement. That is why delta T is different from delta X or delta P or delta E. Now, because of the spread in the distribution, measurements on identically prepared system will not yield identical results. We all are familiar with the concept of the position momentum uncertainty principle, which says that the spread in x is reciprocal to the spread in momentum. And this is due to the wave nature, and it is basically the quantum version of the Fourier uncertainty. And if you are interested, you can watch my last video. And we know that the product of these two, it is greater than or equal to h bar by 2. Now, from where does the relation come from? In quantum mechanics, there is a generalized uncertainty principle. That is what I'm going to discuss now. Suppose you have two observables, A and B. So these observables can be position, momentum, or energy. Now, how they fit together to describe a quantum state? This is given by commutation relation. And this commutation relation, mathematically it is represented like this. I have used a cap on top of A and B, representing that it's an operator. And this relation can have either 0 or non-zero. If the commutation relation of two observables A and B, if it is equal to 0, then we say they are commuting, which means that you can know them together very precisely. But if it is non-zero, then we say it is non-commuting. That means the more sharply you know one of the observable, the fuzzier the other becomes. And this relation, it is mathematically represented by this formula. And I'm not going into the derivation of this formula, but this is what we call as a generalized uncertainty principle. Now, if I want to find the position momentum uncertainty, then I can replace A by position and B by momentum, and the commutation relation of that two quantity, it is non-zero, and it is equal to I into h bar. H bar is the reduced Planck constant. So if you substitute this in the generalized uncertainty principle, then you'll get this relation. And you already know that sigma x is nothing but delta x, and sigma p, it is nothing but delta p. And the lower limit is h bar by 2. Now we have understood all the basics which are required to finally crack the energy time uncertainty principle. So we have this mathematical relation, and we know only energy can have a spread from its distribution, and delta t we need to understand. So for this, let us consider Hamiltonian of the system. Hamiltonian of the system, it gives the energy of the system and also controls how the system evolves with time. So for that particular system, let us consider an observable C. It can be position, momentum, or spin. And we'll also assume that this observable C, it does not explicitly depend on time. Now, the rate of change of this observable C, it is given by this mathematical formula. The term on the left-hand side, it's the time derivative of the mean value of C. And the first term on the right-hand side, it's the commutation relation of observable C with the Hamiltonian. And the last term on the right-hand side, it's the partial derivative of C with respect to time. And we have already assumed that C does not explicitly depend on time, so this term will be 0. Now, in this relation, if C commutes with the Hamiltonian, so the commutation relation will be 0, then the derivative of the mean value will be 0. This says that the observable C, it's a conserved quantity. Now, let us recall our generalized uncertainty principle. So in this expression, you replace A by the Hamiltonian and B by the observable C, then you'll get this relation. Now, if you rearrange this, then we can write it like this. Now, in this formula, sigma h, it is of the order of the spread in the energy, because Hamiltonian gives the energy. And if you see the term inside the bracket, it has the dimension of time. So if I replace these two, I get this relation, which is nothing but energy time uncertainty relation. But the story is not over yet, because we still have to understand what is this delta t. Now, in this relation, if you see the expression on the left-hand side, then we can interpret like this. Suppose if you are tracking the change in the average value of C, and if this change in C is of the order of the standard deviation of C, then that particular time scale is what we are referring to as a delta t. In other words, delta t is a characteristic time scale over which the average value of C changes significantly, say by 1 standard deviation. But how delta t is, or what the value of delta t is, this depends on the observable we are considering. This is why I said in the beginning that the energy time uncertainty principle, it is very different from the other uncertainty relations. Now we have understood what is delta t in the energy time uncertainty relation, and we also found out that delta t depends on the observable we are talking about. And here I'll show you 3 different examples, and where we consider different quantum system and different observables, and let us see how the energy time uncertainty principle looks like. The first is stationary state. So here the observable C can be any time independent quantity. So since it is time independent quantity, so the derivative will be 0. So if the derivative is 0, that means the change in energy also will be 0. Then if you apply the energy time uncertainty principle, then delta t will tend to infinity, which means that the system does not evolve, nothing changes in time. Second example is the unstable particle. And here the observable will be the population of the unstable state. So the time scale where appreciable changes happens will be of the order of the decay constant. So if I substitute this in the uncertainty relation, then I will have delta E of the order of h bar by tau. And this says that the energy spread reflects the instability of the particle. The third example is the free particle wave packets. Here the observable will be the position. See, in the energy time uncertainty, position can also play a role. That is what we are going to see here. So the rate of change of the mean value of x will be given by this relation. So delta t will be inversely proportional to the mean value. So if I substitute these two in the energy time uncertainty relation, I'll get this expression. So from here we can see that the smaller the spread, energy spread or the momentum spread, the slower the evolution of the wave packets. So in summary, the energy time uncertainty is not about measuring time. It is about how the system evolves. And delta t is not the uncertainty in time, rather it's a time scale over which the system noticeably changes, and different observable gives different delta t, but the core idea is always the same. That is, the sharper the energy, the slower the change in the system. Thank you everyone for watching this video.